dealing with shrinking airwaves. Everyone knows that we face the continued reallocation of the frequency spectrum for use by different operators, specifically mobile phone operators. This means that we need to be better at using the space we have left and making sure we have systems that can fit as many channels as possible into this space without compromising the quality of the audio being transmitted. Spectral efficiency. How is Sennheiser responding to the loss of spectrum? There are many lofty claims on the market today about spectral efficiency. Most, however, have chosen to compromise somewhere in the transmission chain to allow this close packing of transmission channels to happen. Usually, the audio is the main component to suffer. As we've said before, here at Sennheiser, we place audio quality above everything else, and nothing has changed, even with the fact that we're having to find ways to allow for the same, if not more channels to fit into a shrinking spectrum. The big problem that we face with wireless RF transmission is intermodulation. This normally happens when you have multiple transmitters in close proximity to each other. When transmitters are close to each other, we find that new frequencies are created by the interaction of the transmitters. This is intermodulation. These new frequencies can cause enough interference that means we are unable to operate on a large number of frequencies due to extremely poor carrier-to-interference ratio. With a conventional system, the only way to counteract intermodulation is to do a full frequency coordination with the objective of keeping the transmitting frequencies spaced so that the intermodulation is not a problem. This, of course, can mean that we could end up in a situation where we face issues with a number of transmission channels we can physically operate. With Digital 6000, we have once again borrowed from the Digital 9000 and have built what we call circulators into the transmitters. These circulators suppress incoming RF energy from other transmitters and make the transmitter intermodulation free. With no intermodulation to worry about, we no longer need to do frequency planning. Instead, we can work with an equidistant frequency grid.
As we have just discussed, intermodulation is a major concern for all operators of wireless microphones. If we can remove these as a concern, just as we have done with our Digital 9000 and Digital 6000, then you will find that working with your system becomes easier and allows you to focus on the show and not on the technology. In this video, we have made a short recording to show you what happens when we have two analog transmitters in close proximity and two digital transmitters in close proximity to each other. In this first section, we are looking at a single analog transmitter. You can see that when we add in another transmitter and slowly bring it close to the first transmitter, how the intermodulation frequencies appear and increase in amplitude. When we recreate this with a pair of digital transmitters, you will see a marked difference in the response. There are no intermodulation frequencies created, allowing us to set up multi-channel systems in an easier way without the worries of intermodulation.
What advantage does an equidistant grid give us? With an equidistant grid, setup of multi-channel systems becomes simple, quick and easy. We no longer need to concern ourselves with intermodulation calculations and can now operate transmitters happily in a denser format than with traditional frequency coordination. Officially, we recommend a spacing of 600 kHz. However, we have seen smaller spacing with no impact on performance or audio quality. Receiver bandwidth. High switching bandwidth of 244 MHz. We have designed the EM6000 as a one-unit-fits-all solution. Therefore, we selected to choose 244 MHz as the operating bandwidth. This means that you have less logistics, as you no longer need to have multiple receivers in differing bandwidth to set up for bigger events. Transmitter bandwidth. Transmitters have less bandwidth than the receiver, to be precise 88 MHz. What's the reasoning behind this? This is completely down to the use of the circulators. The max bandwidth that the circulator can operate at is 88 MHz. This is a very small drawback when you have to consider all the benefits that the circulator will give you. However, it must be noted that the receiver is a full 244 MHz. All you must do is choose the correct transmitter frequency range to meet your regional requirements, and you're good to go. Density. So you have a smaller bandwidth with your transmitters, but a higher density is achievable. How many channels can you fit into the 88 MHz window with Digital 6000? Thanks to the equidistant grid and some simple maths, we can work this number out very simply. 88 divided by 0.6 gives us 146.6 reoccurring. So let's just round down to 146 links with Digital 6000 and Digital 9000. With a conventional analog system from Sennheiser, we would normally only see 30 links in the same space, and with the same high level of robustness. Obviously, this is using the recommended spacing, and with careful coordination, this number can increase. But I think you can see that the difference between Digital 6000 is unmatched. Selection. Integrated 32 MHz selective filters. To allow for even greater selectivity in Digital 6000, we have integrated selective 32 MHz filters into the EM6000. These were already introduced in the Digital 9000, where we placed these inside the antenna boosters. With the Digital 6000, we have placed them in the receiver itself. This creates even more benefit for the end user, some of which we will discuss now, and some which we will discuss a little later in this series. By having selective filters in the receiver, we are better able to ensure higher performance of the receiver in demanding RF environments. This is down to the fact that the filters allow the receiver to only focus on the frequencies that the transmitters paired to it are operating in.